Well, let me start by telling you that this is a very tough problem that I had to solve. It's one of the most exacting problems that engaged me in all my life. Now, to start off with, well, I had many lucky breaks, and I'm going to tell you some of my lucky breaks. One of my lucky breaks was while working for my PhD in physics in Columbia University in 1951. I met a professor from astronomy department named Lloyd Motz, M-O-T-Z. And I had an idea for improving telescope reception. And he realized I was interested in astronomy. He said, hey, come on, I want you to be in the department as my assistant professor. So I became a faculty member in the Columbia University Astronomy Department in 1951. I didn't know any astronomy, so I had to catch up very quickly to learn anything that he was doing because I had to teach in the evening. So during the day, I was learning about astronomy, and at night, I had to teach 3 different sections, and I had access to a telescope. We had a telescope on top of the building. This Pupil building was 13 stories high, and I was supposed to take my students there after class. Anyway, it was interesting. So that's how I got into astronomy. And being in the astronomy department, I had obligations. I had to attend a seminar. So an astronomy seminar in 1953. After 2 years in astronomy, one of the visiting scientists from Yale University, I remember him well, he came up, he knew I was a spectroscopist. So first of all, I have to show you about spectroscopy. And he gave me the challenge. He said, I want you to work, aren't you willing to work on this particular problem? I was stupid enough to say yes. And so I got stuck with that problem that was very difficult. And my thesis advisor, Charlie Towns, was interested in astronomy. He said if I solved the problem, I would get a PhD in it. Well, I'm going to show you the problem. It was a bum steer. It was the wrong idea. Completely different. But it took me a whole year to work on it. I did exactly what he wanted me to do. I made the samples, and I had to make the samples at low temperature, a special spectrometer, and I had to go all the way to Brookhaven Laboratory to do the experiment. We didn't have that equipment. Turned out to be a bum steer. It didn't work out. And I was told, hey, you better work on this after you have your PhD. So I had to go back to my old problem, which was it was a real physics problem, which involved antiferromagnetic resonance and manganese fluoride. Very tough problem too. But that problem also involved doing low temperatures, milliwave radiation, and doing spectroscopy. So the first thing I want to show you is, what is spectroscopy? That's the first thing I want to show you. Now if you look at this, number 1 and number 2, these are 2 examples how you can take just light and examine the light carefully. Now this is not new stuff. This was done by Isaac Newton already 400 years ago. He made the prism, he cut the prism himself, and he demonstrated this particular technique. Now the next slide shows you some commercial equipment. This is commercial equipment. On the left is a very primitive spectrometer. On the right is one that you can buy. Okay. Now, way back, this is in 1825 or thereabout. I mean, we're talking about, at least 200 years ago. Somebody already had a spectrometer, had this instrument, and attached it to a telescope, and looked at the sun very carefully. You've got to do this very carefully. And this is what you see when you look at the sun. You see the complete spectrum, all the way from blue to red, and you see dark absorption lines superimposed. You see these dark lines? They didn't know what it was. 45 years later, in the next slide, they did some experiments on gases, and they found, sure enough, you can identify elements in the sun's spectrum, like calcium, iron, helium, sodium, oxygen, magnesium, mercury, and hydrogen.
Next one. Next slide.
Now, Fraunhofer did this experiment. Shall I do this is better?
Well, no, because when you turn your head, they can't.
Oh, I see. Okay. Now, Fraunhofer, Memsley did this in 1814. It's a long time ago. But 45 years later, they made spectra. Now, this is not too difficult to do. All you take is a flame, you put some salt on it, and you see sodium lines. You see the sodium lines, and they're in the middle. The sodium lines are very pronounced. It's a sodium doublet. And you can identify all the other elements that are in the outer surface of the sun. Okay, so that's how we do spectroscopy. Do you follow this? You all get the idea? Okay. Next slide. Now, what was the problem that I had to solve? What was the problem they gave me? They found that in 1921, somebody was using that equipment and also looking at spectra, but not at the sun, at some other stars. You don't have to use the sun. You can use any star as a background. And they found, sure enough, on that spectrum were sharp lines. Okay, some of them you can identify, like sodium and mercury and so forth. On the other hand, he found some lines that are wide, diffuse, white lines. I've never seen that before. Never seen that. So these were called diffuse interstellar lines. Diffuse meaning they have a width. Very unusual. And there are about at least 200 of them. 200 of these lines. I had no idea where they come from. No idea. Well, that was a challenge. Find out where they are, where they come from. Now we see on the right side the spectrum. This is the complete spectrum with the diffuse lines superimposed. Now they don't look as sharp as this. You don't see them sharp. They all have a width to it. And the width changes. They don't have the same width. Some are very wide, some are just a couple of angstroms. But it's very peculiar. They couldn't figure out what caused that. Where did these come from? Well, I managed to solve the problem, but this problem was very difficult. And let me show you how I did this before I got to the solution. First of all, I was very lucky to get a position in California at a subsidiary of Xerox. It's called Electro-Optical Systems. And I got there in 1963. And I was very lucky to get a contact information from NASA, somebody who worked in NASA, and we had money. So I contacted this guy, his name was Maurice Dubin. He's also Jewish, by the way. And he gave me money. So all of a sudden I had some money to work with. Now, what did I do with the money? First of all, I had no money to pay for a part-time girl, and I engaged a woman to go to Caltech Library every day. She had to go every day and come back with reference papers, publications on spectroscopy. So at night I was losing them, picked up new ones, gave another assignment, she had to go back again. So by the time I finished, I had a huge stack of papers from publications in spectroscopy. I had to find out, well, what is it? Is there anything there, any clues? Is there anything I can use? Well, there was nothing there I could really use until I finally thought about the problem. That's very peculiar. If you look around, you'd see a lot of green. Where does all that green come from? So it reminded me of an interesting story. When you see a lot of horse shit manure on the ground, you know there has to be a horse someplace. So I knew there had to be a place where these molecules are made. So all of a sudden, I got from millions of possibilities, and by the way, I also hired 2 part-time students who did nothing else. One of my students were technicians, 2 technicians who worked on a problem, and I gave them all kinds of chemicals to survey. So I did experimental work, and it took me about 3 years. For 3 years, I zeroed in on the right molecule. I knew it had to be something consistent with chlorophyll, but it wasn't chlorophyll. It had to be something more basic than chlorophyll. Now we have hundreds of these things to check on, and I give you an idea how you check on it. Here's one example I showed you. You can see the molecule at the bottom there. That's the one I identified. That's the critical part of chlorophyll. It's the center part. I'll explain to you what it does. Now, here you'd see 4428. You see the center line? That's the strongest signal of the diffuse interstellar bands, the 4428 angstrom. There's really nothing more bluer than this, but there are lots of others beside. Now what you have to do is to match it. Look how I matched it. The red is the Sorey band from this molecule, and the black is the astronomical data. Look how they check. Do you see that? They overlap. That was I had to do with hundreds of these structures. They all had to overlap just like that. That's not an easy task. It took me a little time. Meantime, I was very lucky to get a position as chair of the physics department at Cal State Fullerton, California State University, in 1971. So I could move there, and I got permission from the government to move my equipment to the university. That's a very big break. So I could continue my spectroscopy at the university using students. So I did a lot of experiments. Now all these experiments were not easy. They were very tough experiments. I had to make the sample. I had to have an equipment that you can lower the temperature to almost absolute zero. So there's a dewar. The sample had to be inside the dewar. I had to get all the liquids to lower the temperature. Then you take the spectra and you look at it. And I did this many, many times. And I could prove that I had the right molecule. All right, now here's the molecule in detail. Let's go over this so you can see what the molecule is all about. You notice the central structure is a double single bonds. And the, let me go around there. You see where I can walk around. I want to show you the detail. This is tough. The electron spins around like this. Spins around. That's what is the critical point of the chlorophyll molecule. In other words, it can absorb solar energy. Now, in the center is the magnesium atom. Now, if you replace the magnesium atom with an iron atom, you have heme. Heme is the blood, center of the blood molecule, it's in heme. So it's the same idea, it works also with blood. You can also use blood as a substitute for chlorophyll. However, chlorophyll is a very complex subject, and it has all kinds of things attached to it. It's not a clean molecule like this. It has all kinds of things attached to it to make it fit into the structure. So chlorophyll, however, has all the atoms of chlorophyll just like that. The center is always magnesium. And for the blood molecule, heme, is iron in the middle, iron, but it has also the same structure. So both systems would work. Now the next stage that I want to share with you takes me now to a medical application. While at the university, one of the technicians for the company called Spectra Physics, the name of Schultes, contacted me, and I worked with him, and I was able to purchase for the department a laser. A laser is a very expensive piece of equipment, and it was not easy to install. It required special water cooling and special high power electricity. And this laser was a tunable laser. I could tune it to any frequency I wanted. Very good. Then I realized that there is a medical problem that maybe I could use. I could use this equipment. I then contacted UCI Medical School in Anaheim. I went to see the head of the department, and I asked him whether he's interested in doing research on cancer. Cancer. Cancer is a very miserable disease. I knew they were working on it, and I knew that this system could be used for cancer treatment. Sure enough, he said yes, but now comes the big problem. How do I get my equipment to UCI Medical School? That equipment was very complicated, and it wasn't easy to transfer. I needed the permission from the president of my university and the president of UCI, both working together to arrange this transfer. So finally, this was not easy to do. I got the equipment to the medical center. Then I was told, you got to work on cancer patients. These were terminal cancer patients that have resorted all possible treatments. They had radiation, they had chemotherapy, nothing worked, and so they're willing to be guinea pigs for this new technology. I found out that, yeah, this technology can be used if you have a right porphyrin. Now, I didn't have the porphyrin. It turned out that porphyrin was discovered by somebody in Buffalo, New York, and it was a blood. It came from an animal. It came from a bovine extract. They used the blood of that extract, cleaned it up, and then called it HPD, hematoporphyrin, porphyrin. And that porphyrin solution was the key to this treatment. So what the doctors did, can you hear me okay?
Yeah.
So what the doctors did, they gave the patient that had to be treated an injection on Monday. Now it turns out the cancer, I didn't know whether you knew this, cancer has a very poor system of getting rid of stuff. They get things inside, and it stays there much longer than for normal cells. So you take advantage of it. So they got injected on Monday, and on Thursday I had to go to the laboratory, to the UCI Medical Center, get the equipment to work. I had to make sure it gets the right light, the right frequency. Not any frequency, it had to be the 6900 angstrom, had to be the red beam completely just went. Now the doctor in charge, I wasn't an MD, I just a PhD. He put a circle around the cancer, and he had treated patients that the cancer can be seen, like breast cancer, cancer from the thread, all kinds of cancers that you can expose. So sure enough, I was told, treat this. But now this is not easy to do. I had to calculate how much intensity, how much to give it, I had to get the right wavelength, and then impinge that light on the cancer. And then you had to wait a week. After a week, the patient came back, and sure enough, the cancer was dead. It's gone. It really killed the cancer. It's an incredible technique. It works on all cancers that are accessible to light. So anytime you have cancers, this can be used. You have to ask the doctor for the treatment. It's called photoradiation therapy, PRT. Now the latest idea is to use this technique for skin cancer, which is much more prevalent. Now for skin cancer, you don't have to wait 3 days. You can just wait a couple of hours, get the injection, it gets to the cancer, and then you put light on it, and it kills the cancer. Can you imagine? That is much easier than chemotherapy, radiation therapy, and all this other shit they're doing, these people. And by the way, that doesn't save their life, it just extends it a little bit. They still will die, and they live a few months longer. It's not a good system. That's the system they're using. So now they have an alternative, which is much better. Now, the government finally approved it. It took them 10 years to finally approve this technique. And now it's standard technique. You just ask for it, every doctor knows about it. And now what molecule do they use? They don't use the blood molecule now. They're using a molecule similar to what I discovered. You see, mine is a much cleaner molecule. Yes, you cannot use it in a pure form. You have to attach some other stuff to it to make it accessible. But it is a much better form than a blood. Anyway, it's now standard technique, photoradiation therapy. Now this shows you, if you look at the whole business, the doctor that I work with, his name is Alan Weil, I'm sorry, and the equipment is in front of me. Now this equipment, you see the equipment? The equipment had to be tuned up to get the right light. I had to calculate how much light I should give it. In other words, how long the exposure. It was usually around 40 minutes, less than an hour. And then they came back a week later and found out the cancer vanished. It just fell right off. It's a very successful treatment, photoradiation therapy. This tells you a little bit about the details, the people I work with, and also I mentioned Thomas Doherty. Doherty was a chemist at the Boswell Park Memorial Institute in Buffalo, New York. I must admit to you that my mother was one of the patients at that hospital. She was willing to volunteer to get this treatment. Kind of a sad story because the treatment was used on her during, she had colon cancer. Colon cancer is a very deadly disease. So in order to keep it working, they left some of the fibers inside the body so she could come back a month later and get more light, more treatment. And sure enough, they cured the cancer. But here's the problem when it's inside the body. That's a very sad situation because you now have dead tissue. And dead tissue causes an infection. And how do you treat the infection? antibiotics. My mother got lots of antibiotics. And what does that do to you? It kills your kidneys. So she died of kidney failure. That was my experience. And because of that experience, I started working at the medical facility on this treatment. So I had personal experience seeing how this works on a patient that is ordinarily would be fatal. Unfortunately, my mother didn't refuse. She should have had a chance of colonoscopy, and she refused it. And that was a big mistake on her part, because she didn't get colonoscopy. They didn't discover the cancer. So don't forget, colonoscopy is a very important precursor to making sure you're okay. So I learned my lesson. Also, it was a sad experience because I visited that facility. I saw how they were treating patients. It was a very sad situation to walk around there. That facility, Roswell Park, you know, I stayed there a couple of weeks. I saw the people walking around with their bottles of chemotherapy. It's kind of sad. So that facility is specialized in just treating cancer. Now, the department where I worked with, UCI, published the results. This is a publication. Now, all kinds of people put their names on the paper because it's a very successful and important discovery. So they all put their names on it. There was Burns, and then you see Dahlman. Ellen Weil was the first one, the doctor I worked with. But there were two Burns, B-U-R-N-S and B-E-R-N-S, and some of them were working at UCI. Since they had the inside track, they had a chance to get their name on the paper. I published my stuff in 2006 under the Spectrochemical Acta. It's called Diffuse Interstellar Bands and a Laboratory Study. This was a big deal to get that thing published and to get all of my results in that paper. This was not an easy project, but I'm glad to share with you that it has a very good application. Now, I've now finished the essential parts of my talk, and I'll give you a chance to ask questions. However, the questions we'll have to either write them down or you have to
I'm
tell
gonna
me
hand
what
them the
they are,
microphone.
and then I'll try and explain it to you.
All right, you wanna sit down?
Yeah.
Okay, and I'll go out and anyone have any questions? Larry?
Yeah.
Hold on. Just give him a minute. So everyone can hear you.
Okay. My question is it applicable to skin cancer? And that's number one question. The second one, what wavelength are you using?
Is it applicable to
skin cancer.
skin cancer?
Yeah, sure.
And what wavelength are you using?
And what wavelength are you using?
If you use a blue laser light, a special laser light, the cancer will fluoresce. It's a good question. That's how you discover it. It fluoresces, you can see it shine. So this technique can be used to identify cancer.
Repeat that, will you please?
He says it fluoresces so you can see the cancer.
Okay.
And then that's when you take the blue.
Then you can treat it.
Treat it.
I've just been treated. I have. It was just less than a week ago.
He said he was just treated a week ago.
Wow.
Any other questions?
You know it works.
Well, it's not with that. He just burned it off with liquid nitrogen.
Fred, this is interesting with regard to cancer. I was in chemistry and we used lasers and ultraviolet light and various other spectrums of light as a mechanism through which to identify chemical compounds that we were that we were researching within the cell structure. My particular area of interest was mRNA, which is the messenger RNA contained in the cell that is put there by transfer RNA from the nucleus into the mitochondria of the cell, which is the language which tells your body what it's going to be. And without lasers and the light, to identify these compounds would have been impossible. That was the thing, because when you're working with compounds, you always have different wavelengths, you have different spectrum of light, and you don't know whether you have a pure compound or not until you have exposed it to this light and analyzed the spectrum that it emits from. Just add a comment.
Very good. I understood it. It's very good.
Anyone else?
Anything else? Anybody else?
Anybody?
Nobody else?
Well, you know where he lives, so if you think of something,
Well, I'll be here, so if you want to ask me personally, I'll be happy to.
It's a pretty
to
remarkable.
show you
Did you
some-
get a Nobel Prize for it,
Wait a minute.
for your
I have-
discovery?
wait, Selma, go ahead, talk into that.
I just wonder if you got a Nobel Prize or some prize for discovering this.
Did you get a Nobel Prize for discovering?
No.
You have to propose it, somebody has to propose it.
The title of your
Talk into
presentation,
here.
the title of the presentation is a molecule that's been discovered in space. I didn't catch that.
I didn't discover the molecule, I identified it. The molecule was already there, according to my wife. I just identified it. I showed what it was. Now, I didn't tell you all the details. It's much more sophisticated than just the molecule. Because the molecule, just like you do in chemistry, doesn't sit there by itself. It is surrounded by other stuff, even in outer space. Now, since I've been here, let me just tell you the next stage. You ask yourself, where are these molecules made? Let me ask you the question, where do you think they're made? They're seen all over the universe, and every direction we look, we see it. So there has to be something that is very similar wherever you look, right? What would that be? That means every solar system has a similar setup like we have. Well, that gives you a very good clue. So you got to find out exactly how our system works. Nobody had done that before. Are you aware of the fact how stupid astronomer is today? You don't have any idea how stupid they are. They have no idea what's going on. No idea. The system in our solar system is very sophisticated. And we can find out where they're made. You know where they're made? In comets. The comets make organic molecules. And these comets,
Fred, I have to admit that I was attracted by the comment about molecule from space. I am very interested in spatial molecules and the kinds of compounds that are formed in space, and we have atoms that have been added to our periodic table in chemistry in the last few years that have very short half-lives that have been discovered from space. And they occur and they land on, we always thought everything that was used in the construction of Earth originated on Earth. Well, apparently it didn't. And so in researching these molecules, I was interested in your molecule and what its half-life was, what its family of compound reactivity, in other words, the other compounds that it reacted with favorably in most cases, and where it liked to make compounds, and to see, I like to find out how things work, why they work, and what makes them work.
Very good. Well, we're very lucky to have some people here in the audience who are very aware of this. I know that at least 2 books, I've published this stuff. 2 of you people have my books. They never read them. In fact, I've sent copies of these books to all the people in NASA. All the key people in NASA have a copy of my book. Do you think they opened them? Nobody even bothers to look at it. It turns out, let me just tell you one thing about what I've discovered. I mean, I made some very important discoveries while here. This was just an earlier one. The discoveries I made while here are completely different. I found out that our solar system is surrounded by a planetary nebula. Nobody was aware of this. It is 80 angstroms away from us. And it is in these planetary nebula that some of the molecules are stored, because the planetary nebula goes around like this, and it has millions of these comets. They're all going like this. They're all going around. Since they're going around, they have a speed. So if you want to identify the molecules, you've got to take care of the speed. That's a Doppler effect. So that gives you a clue of how fast these molecules are being emitted from the comets. Now, we do have spectroscopy, isolated spectroscopy from these comets in our solar system. So there is a connection. We can actually identify some of these organic molecules that come out from a comet. Can you imagine? That is a very important clue. Now, the interesting thing is to look at this. We are just one solar system. There are millions and millions of solar systems. Do they all work similar to us? Yeah, they're very similar, but some of them don't work. If they don't work, whoever is in charge of this whole system, we call God or the guy in charge, there has to be some place where these things are started off. Nobody ever thought about this because we don't have the answer. We don't know where this person is, whether it's a person or not. It doesn't have to be a person. It could be a group. I don't know what it is. But it has something to do with our religion. I don't want to get into that in detail because it's very messy. But they don't understand it either. They don't understand it.
I had the good fortune of living in Temecula, and right nearby is not too far from Palomar Observatory, which is on the mountain behind Temecula, up on the skyline, the range of hills behind Temecula. And I was, since I was interested in microscopy, I was interested in the resolution and why these microscopes couldn't resolve the difference between planets, things as large as planets, even as far away as they are. I couldn't understand the absence of the ability to resolve the differences. But the problem, it turns out, that when you're looking out in space, that one thing may be near one planet and the other is 20 or 30 light years on out beyond, and they look like from here that they're right together. Well, when you begin to realize how far the second, you begin to realize the problem with resolution.
Interesting. Well, we're lucky we have some people in the audience who are up on stuff. I had no idea. I had no idea.
Thank you very much for
I should
coming
also
today.
tell you this. When I was trying to solve the problem, I want to share this with you. When I was trying to solve the problem, there were millions of possibilities until finally I saw chlorophyll. And then I finally got hold of a book. This book is on porphyrins. It just gives nothing but porphyrins. So here I had to look at the book to find out, hey, what's behind these porphyrins? And this book lists all the porphyrins that were known for at least 50 years already. It's the old stuff, it's all published stuff. So from there, I was able to get the simpler program that you saw over the picture. So that was a very important clue, having discovered this book. Just one book.
What is the
So
name of the
instead of
book?
million possibilities, I was down to just a couple of hundred.
Thank you very much, Professor. That's wonderful.
Thank you so much for listening. If you have any questions, come and see me.
Okay.
Thank you, Sheila.
Yes, of course.
What is the makeup of the module? What is the makeup of the module?
Bernie, I gotta give you a microphone, you can't hear you.
I don't remember exactly, but it's.
You have to talk into it, you can't hear you.
What is the makeup of the module?
Can't tell you more than that because
What is it made of?
The makeup.
Say it again. Say it
It's
again.
called magnesium
Well, the
tetrabenz
porphyrin is
sulfur.
simply
Magnesium
emitting a certain, because it's part of the compound, it emits a wavelength which identifies that as
Magnesium
porphyrin.
tetrabenz sulfur.
And that also identifies the molecule in which it's incorporated. Yeah, and those things, because the chemistry of cancer is that
And I asked Annie to make a glossary of all the difficult words, and she didn't.
malignancy that grows and grows.
If you have a glossary of what everything
Well, when you introduce a
he's
compound,
talking about, you know what he's talking
I can't grow
about.
anymore with it. This doesn't help you grow. That it can't, and it will revert to the natural immune system of the body, which will then eliminate and get rid of it